We always hear that machines learn by making mistakes, but what does that actually mean? Well, it's not random trial and error. It's a super calculated mathematical process. And today, we're going to pull back the curtain on one of the most fundamental principles behind it all, empirical risk minimization. This thing is basically the engine that powers a ton of the AI you use every single day. So let's dive right in. So yeah, that big question. How do machines really learn from their mistakes? It's not like us, right? There's no feeling of regret or a promise to do better next time. It's all about a cold, hard, mathematical process for finding patterns hidden inside of data. And honestly, if you can wrap your head around this one concept, you're going to have a much, much better grasp on how modern AI actually ticks. All right, let's get into the goal of all this learning. Think of it like a blueprint for building something. Imagine your job is to teach a machine to predict something, anything really, about the entire world. Maybe it's spotting spam emails. Maybe it's guessing stock prices. The catch? You can't show it the whole world. You can only give it a tiny, tiny handful of examples. And that is the fundamental challenge of machine learning. How do you build a model that can look at a small sample and then generalize, make accurate guesses about the big, messy, complicated reality out there? So, to tackle a problem that huge, any learning algorithm needs what I like to call a builder's toolkit. First up, you've got your training set. Think of this as your small sample of the real world. It's the only piece of ground you get to build on. Next, you have the hypothesis class. This is like your catalog of all the possible blueprints or models you're allowed to build. All your options are in here. And finally, you have the loss function. This is your measuring tape. It's how you figure out how wrong or off any of your predictions are. These three things, the data, the blueprints, and the measuring tape, they are the absolute foundation for everything that comes next. Okay, so with our toolkit in hand, we move from the planning phase, the blueprint, and head into the workshop. And the guiding principle in this workshop is actually beautiful in its simplicity. It's almost just common sense, really. You look at all the possible models you can build, you try each one out on that small set of data you have, and you simply pick the one that makes the fewest mistakes. That's it. That is the entire idea behind empirical risk minimization. Simple, right? And this diagram right here, it lays out that entire process perfectly. Let's just walk through it together. Over on the left, you've got the raw material, our training data. In this case, it's a simple list of people's heights and their gender. That data gets fed into the learning algorithm. Now, the algorithm's whole job is to dig through its toolbox, that's the hypothesis class, and test out every possible rule it can think of. And for every single rule it tries, it uses that measuring tape, the loss function, to see how many mistakes it made. Its one and only goal is to find the single best predictor, the one you see on the right that has the absolute lowest number of mistakes for this specific set of data. So what the algorithm is really trying to do is minimize something with a fancy name, empirical risk. I know, it sounds super technical, but trust me, it's not. It's just the formal name for the average error the model makes on the training data. A good way to think about it is like the model's report card, but it's only graded on the stuff it was allowed to study. The entire point of this whole process of ERM is to get the best possible grade on that internal test. So what did all that work give us in our little height and gender example? Well, after checking all its options, the algorithm landed on one simple, elegant rule. The single best predictor it could find was just a height threshold. If a person is taller than 167.4 centimeters, guess one way. If they're shorter, guess the other way. That's it. That was the one rule that made the fewest mistakes on the data it had. Okay, so this all seems pretty solid, right? Just find the model with the fewest mistakes on your training data. Seems like a foolproof strategy. But what happens when a model is too good? What happens when it gets a perfect score? Well, this is where things get super interesting. It's time for the real-world test, and we're about to see how being an A-plus student in the workshop can sometimes make you a total failure out in the real world. To see what I mean, let's invent a new kind of model. It's super powerful, and we'll call it the memorizer. Its strategy couldn't be simpler. It just perfectly memorizes every single piece of data you show it. It has a photographic memory. If you ask it about someone from the training set, it nails it every time. But what happens when you show it a new face it's never seen before? Well, that's where the story takes a turn. And what's the memorizer's empirical risk? Its training error. It's a big, fat, perfect 0. According to that internal report card, it didn't make a single mistake. It aced the exam. On paper, this is the best possible model. You literally can't do any better than 0 mistakes. Or can you? And this gets us to a really deep question, not just about AI, but about intelligence itself. Is just memorizing a bunch of facts the same thing as actually learning a concept? Is a perfect memory the same thing as being smart? I mean, think about it. What do you think is going to happen when we take this perfect model and show it a person it's never, ever seen before? And here it is, the big reveal. The memorizer, our perfect model with a training score of 0, is an absolute total disaster in the real world. Its error rate on new data skyrockets to a whopping 80%. But get this, our other, simpler model, the one that actually got a 20% error during training, a C grade if you will, it's just way better. Its error rate in the real world is also 20%. And that's the difference. The simpler model actually learned a general rule, while the memorizer just, well, memorized the answers to the test. And this quote from the source material just hits the nail on the head. It says, if the hypothesis class is excessively rich, empirical risk is not a good proxy of the true risk. Let's break that down. Excessively rich just means your catalog of blueprints is way too big and complex. And if that's the case, then the score your model gets in the workshop, the empirical risk, is basically meaningless. It tells you nothing about how well it's actually going to work out in the real world. So how do we stop ourselves from building these useless memorizer models? Well, the first step is to understand where mistakes or errors even come from in the first place. It's time to do a little damage report. Let's look at the anatomy of an error. Now, this chart is really important. It shows that a model's total error isn't just one single thing. It's actually made up of different pieces. You see those gaps between the vertical lines? Each one tells a story. That red line on the left, the Bayes line, that's the absolute best anyone could ever do. It's the limit set by pure randomness in the world. The green line is the best score that your chosen type of model could possibly get. And that black line on the right is what your final model actually managed to do. The gaps between them, that's where the different kinds of errors live. So what are those errors? Well, there are 3 main types. First, you have approximation error. That's the gap between the best possible score and the best your type of model could ever get. Basically, it means your blueprints weren't good enough from the very beginning. Second, there's estimation error. This is the gap between the best your model could have done and what it actually did. This happens when your limited training data tricks you into building the wrong thing. And last, you have the Bayes risk. This is just the unavoidable background noise of the universe. It's the randomness that no model, no matter how smart, can ever predict perfectly. Okay, so now that we know what the different kinds of errors are, how do we actually control them? How do we build models that truly learn instead of just memorizing? Let's get into our final act here and lay out the principles for building things that last. So how do we fix this problem of the workshop test not matching the real world? Thankfully, there's a powerful mathematical idea that gives us a guarantee. It basically says this: as long as your collection of blueprints, your hypothesis class, isn't insanely complicated, excessively rich, then your training error will be a good predictor of your real-world error. It's this beautiful principle that makes the whole process work. It ensures that the grade you get in the workshop is actually a fair preview of how you'll do on the final exam. So at the end of the day, what are the big takeaways? What are the rules for good building? The source boils it down to 3 key steps. Step 1, still aim to minimize your training error. That's still the right place to start. Step 2, get your hands on as much training data as you possibly can. The more examples you have, the harder it is for the algorithm to get misled. And step 3, and this one is absolutely crucial, use what you already know about the world to limit how complex your model can be. Don't even give it the option to become a memorizer. Force it to choose from simpler, more sensible blueprints. So really, this whole game of machine learning comes down to this incredible balancing act. On one side, you need a model that's powerful enough to actually find the real hidden patterns in your data. But on the other side, it has to be simple enough that it doesn't just start memorizing all the random noise. And that leaves us with the big, multi-billion-dollar question that researchers are still tackling every single day. For any given problem, how in the world do you find that perfect, magical balance?